Today I would like to talk about applied aerodynamics, aerodynamic coefficients, their magnitudes and variations. It's not so big part of our discussion in chapter 1, Introductory, and probably today we will finish a bit earlier than usual. And after this presentation, I would like to give you some examples about calculations. Next time on Thursday, we will start chapter 2. And on Friday, I will give you some information about making work 1, how to process data, how to present data, some techniques that I consider interesting and important to share with you. Last time we talked about the various concepts about types of flow, general introduction, and another one general introduction about types of flow. We talk about viscous flow, boundary layer, different types, right? Thermal boundary layer, dependence on temperature and viscosity, thickness on the boundary layer, laminar and turbulent. And today we continue talking about aerodynamic coefficients. I would like to remind you that aerodynamic coefficients, they are parameters that describe in dimensionless form relations on forces in aerodynamics and are quite important to compare different bodies, different flow conditions, performance. Since we are talking about drag and drag coefficient here, I would like you to write for you this formula for drag coefficient. Probably it would be better if I turn off camera, so would be improving the quality of video. So CD in general is D divided by Q infinite S, right? Where D is drag, Q infinite is the dynamic pressure, S is the reference area. In case of plate, it will be a size of plate. In case of cylinder, it will be diameter of cylinder. In case of airfoil, it will be thickness of this airfoil. In some airfoils is the chord size, but in this particular case, it's the thickness of the airfoil. And for cylinder, okay, diameter, and no other types of bodies. Quite simple bodies. Some bodies we can see here have relatively big value of CD coefficient. Bigger drag coefficient, it means bigger value of drag per dynamic pressure and per size. Flat plate has the biggest value possible of the drag coefficient. This drag coefficient for flat plate is equal to. What does it mean? It means that drag force is 2 times bigger than product on dynamic pressure and area. CD coefficient equal to. If you remember, also one of the previous lectures we talked that drag and other aerodynamic coefficients, they are not just functions of one parameter. They are functions usually of 2 or 3 parameters. They are Reynolds number, they are Mach number, and angle of attack. Here in this schematic, in this picture A, we have just defined Reynolds number. Reynolds number 10 powered by 5. For various, for different Reynolds number, this drag coefficient also can change. And since our flow is considered incompressible, we consider that Mach number is equal to 0. Even though if velocity is not 0, we consider Mach 0. Size of plate and the angle of attack here is 90 degrees. CD equal 2 is a very big, an extremely big number of drag coefficient. With such kind of drag coefficient, we cannot build any kind of airplane or aerodynamic vehicle that would be flying, right? Because we need to have thrust of engine 2 times than how to say, weight, or at least. So it's not, absolutely not worth to work with this kind of structure. But we need to know these structures, and we need to know the possible highest possible limit for drag coefficient, because in several applications we might use them. For example, in case of deceleration, in case of braking, re-entry back to atmosphere, and other applications when we need to transform kinetic energy of flow into just thermal energy in the most efficient way. This is done by a perpendicular flat plate that transforms all flow velocity into such a highly turbulence volume where all energy is dissipated and transformed to temperature. So CT2, consider this as top, is the highest possible value of drag coefficient. Usually all drag coefficients for other bodies, they have smaller values. For example, for cylinder, case B, cylinder diameter D, drag coefficient is equal 1.2. Already almost 2 times smaller. It happens because cylinder has better flow organization, and turbulence intensity behind cylinder is much smaller than turbulence intensity behind flat plate. Okay, it's more smooth from point of view of flow, and flow goes around this cylinder in a better way. So it creates smaller volume of intense turbulence inside. But of course, having cylinder is not possible to create an efficient aerodynamic body. We know that to fly, we need to have a body that creates significant lift and has a relatively low values of drag. Lift is going opposite to weight of the airplane or other aerodynamic body. And this is the force which is intentionally created, right? But always we have drag force in any case. In case of cylinder, in case of airfoil, always. Just the question is how good is the relation between lift and drag. I would like to remember you that main criteria for aerodynamic efficiency is ratio between lift and drag, L to D ratio, and it's same as CL to CD ratio. Okay, as we saw previously, right, these forces are ratio between forces is equal to ratio between aerodynamic coefficient, because they are both referenced to same reference force. Streamlined body has a drag coefficient approximately 10 times smaller than cylinder of same size. We can see in case B, cylinder of this diameter and airfoil of same thickness have approximately 10 times different losses or drag. This happens because flow around airfoil is smooth and does not create such a big area or volume of turbulence. So turbulence area is small behind this airfoil. We can compare also this airfoil with a cylinder of 10 times smaller, is case D. In this case, we might see small cylinder that has 10 times smaller diameter, and it creates same level of turbulence as the airfoil. For cylinder, we know already that drag coefficient is known, so it's independent on size. Just when we convert this drag coefficient into drag force, we will see that drag force for airfoil and drag force for this 10 times smaller cylinder, they are having same value. Drag coefficient is smaller, right, 10 times for body, but because body is 10 times bigger, drag force is same. So this shows significance and importance of design of aerodynamic bodies that allow us to use big profiles, long profiles of airfoils, creating significant values of lift, and same time having very small drag force, very small drag force. Case E shows a cylinder of diameter D, same as we had in case B, and it has 2 times smaller drag coefficient. We might see that this CD is equal 0.6. Difference between case B and case E are the Reynolds number. Okay, there are different Reynolds numbers, and because of this structure of separated zone, structure of turbulence is different. We see that in higher Reynolds number, zone is smaller of turbulence, and this results in significant reduction of drag coefficient. So we can conclude here that cylinder works from aerodynamic point of view better at higher Reynolds number. Okay, higher Reynolds number. Now, what is the Reynolds number? Is the ratio, right, between velocity, density, and size divided by viscosity. So we have to in some way increase this Reynolds number, or we increase velocity, or we increase diameter. We cannot change air, right? We cannot substitute air, because if airplane flies in air, it will be same value, almost same value of density and viscosity for same altitude of flight. So we cannot control these two parameters, but we can control velocity and size, diameter. In such a way, we can significantly control the value of Reynolds number, and by this, we also control drag coefficient. So typical values of drag coefficient for plate is biggest, right, equal to. For cylinder can change depending on value of Reynolds number. Okay, for plate also changes. It's also true. For cylinder changes, but smaller, around 2-3 times smaller. Can be 0.6, can be 1.2, can be smaller than these values, can be bigger, depend on Reynolds number. We can find information on this function in the literature. I think in some part of our lecture we also have, maybe not today, but other time, we have this diagram, and it's very simple to find in internet. And for a streamlined body like airfoil, drag coefficient is significantly smaller because it optimizes flow around in order to reduce losses in the flow. Okay, So we see different values of drag coefficient, different values. But not just the values are important. Also important is the source of this drag. In case of cylinder, case A, as you may see on figure 155, in case B cylinder, sorry, and case A flat plate, we see that drag force is created mostly by pressure. This white zone here is pressure influence or pressure source. Here on this legend, you can see that white zone is pressure drag or a drag created by pressure forces. And this gray zone is skin friction drag created by viscosity and skin friction. Okay, this here. For plate and cylinder, most part of drag is pressure source. Okay, and if we see this for airfoil, for example, we see that the most part is created by skin friction. Most part is created by skin friction. Sorry, I put here just viscosity. Probably is not so much correct to put. Would be better to put tau symbol, skin friction coefficient. Okay, and for airfoil is the most source, the biggest source is the skin friction, and the smallest source, very small here, is pressure influence on the drag. This relation between pressure and skin friction influence on drag gives us possibility to determine two different types of bodies. There are bodies which are mostly created by pressure drag. They are called blunt bodies. And there are streamlined bodies where the most of the drag is skin friction. They are called streamlined bodies. These bodies are airfoils or wings. Just a moment. Okay. Airfoils and wings. Streamlined body, skin friction is the main source of drag, and blunt bodies, cylinders, plate, and similar bodies where the most influence on drag is pressure. Why it's so much important, why we see this right now? Because as we saw previously, it's quite simple, usually quite simple, to predict distribution of pressure. For example, using Bernoulli equation, that is inviscid Bernoulli equation, simple one, we find the relation between velocity and pressure. You remember that it's constant for all points inside flow, because flow is adiabatic, there is no friction, right? And there's entropic. So this equation of Bernoulli works quite well. And pressure is simple to determine. Pressure is simple to calculate analytically. So we can calculate also drag analytically in such way. We will see that very soon when we describe models of flow, in particular application of flow equations to blunt bodies. We will see how simple can be to calculate analytically this pressure distribution and how simple at the end would be to calculate drag. Just integrating pressure distribution, right? Because viscosity here is a very, very small part, which is can be neglected. In opposite, when we are talking about airfoils, we see that pressure has very small, or pressure distribution has very small impact on streamlined body. In this case, we need to consider shear stress, and in some way we need to determine shear stress to obtain drag. We saw that shear stress is difficult to calculate, even looking to previous example when we just few pages before. I will try to move to our previous calculations. One of the previous calculations, where is somewhere before? Just a moment, I will try to find this example here. You remember, I hope. This is an example where we had to calculate axial force and force coefficient. Pressure is quite simple to calculate. It's constant everywhere. But shear stress is very difficult to analyze because its nonlinear function can be obtained experimentally or numerically, but almost never can be obtained analytically. It's not possible. So when we see that most part of drag is formed by this nonlinear function, which is almost impossible to calculate analytically, we understand how difficult to obtain drag for the airfoil, because this function is not known for arbitrary airfoil. Aerodynamics is trying to find ways to calculate this distribution of shear stress for airfoil, but not so much, not so many models exist that could accurately predict this shear stress distribution. This is why calculation of drag and drag coefficient analytically on airfoil is an extremely complex problem that cannot be done for arbitrary airfoil or even for arbitrary body. This is difficult, but we can do a lot calculating lift. And this is also very important thing that we will work on. Here we may see distribution of shear stress or friction coefficient, let's say. Friction coefficient is purely shear stress divided by dynamic pressure multiplied by C. It's okay, let me extend here. This D prime is something that can be calculated similar, or let's say similar to tau divided by Q infinite. Okay, shear stress divided by dynamic pressure. As you may see, this is experimental data. It's not obtained analytically. It can be approximated analytically, but cannot be calculated purely analytically because boundary layer, especially turbulent boundary layer, has equations that cannot be solved analytically, can be solved only numerically, or can be provided experimental study on this question. For example, here we may see same boundary layer, but it propagates in space. Here, one axis is Reynolds number, and the other axis is friction coefficient. This Reynolds number has a C, which is basically coordinate on the plate. It's a coordinate on the plate. We see that initially boundary layer is laminar at some region, right? And then there is a transition zone, so-called transition zone. This transition zone can happen in different way. It depends on several parameters that are not introduced here. For example, quality of surface, conditions on temperature, maybe other aspects like initial level of turbulence. So transition can happen in various forms, okay, various ways. This is why there are several curves of transition here. And then it happens turbulent flow after. So laminar flow always transforms to turbulent flow somewhere in the middle between 10 powered by 5, 10 powered by 6 Reynolds, this boundary layer becomes turbulent. Okay. We will see last chapters of gas dynamics, last lectures of gas dynamics, talking in particular about models, analytical solutions, and numerical solutions on the flow for laminar boundary layer and for turbulent boundary layer as well. This is a topic of at the end of gas dynamics, at the end of the book. If you are interested right now, of course, you can study, and in some of future lectures or practical classes, we can also discuss this topic for people who are interested to study in advance something, for example, to perform better quality simulation in work 3 of aerodynamics. But it's not obligatory for aerodynamics to go deep in study of last chapters of the book. Not now. In gas dynamics, we have to do it obligatory. Variation of drag coefficient with angle of attack and with the lift coefficient. We know that okay, there is a relation that we might write that CD is some function of angle of attack. You might see it here that we know that also CL is another function of angle of attack. So combining these two functions together, since they have same parameter in common, like parametric function, we can write CD. Oh, sorry, sometimes I have problems with this writing. Is a function of CL, which is shown also here. Dependence on CD and CL, I hope you remember, is not, dependence on CL and alpha is not so complex. We already had it before, and we will have still very soon. It's like this, alpha CL. We see that in the most part curve is linear. So we see this kind of linear dependence, and only at high values of angle of attack we have flow separation, and we have maximum value of angle of attack corresponds to CL stall condition, and alpha maximum. Usually drag coefficient has its minimum. As I told you, this is a variation for 5-digit airfoil for Reynolds 3 million. For other values of Reynolds, curves are similar, but as I told you, that is highly dependent on this CD variation is highly dependent on shear stress distribution, and shear stress strictly related to Reynolds number. So for different Reynolds number, this drag function will be different. It's just one case possible. If you are interested to see others, you can visit, for example, NACA website, where variation of drag coefficient for different Reynolds number are shown. I think it's quite popular. Probably on Friday we can see these graphs. I will show you as an example. There are others. We cannot say if drag coefficient increases or decreases with the increase or decrease of Reynolds number. For each aerodynamic body is different, but it changes. It definitely changes. Drag coefficient is always positive, cannot have its negative values. Drag coefficient has minimal values at small angles of attack, near 0, 5 degrees, somewhere there. Other possibilities, other minimums of these functions, but always close to 0. Usually airfoils are designed to provide minimal angle of attack and minimal value of drag coefficient and this small angle of attack. Okay, and at positive and negative angle of attack, drag coefficient increases. Typical value of drag coefficient for airfoil is 100s, 200s of units. So not so big values. You remember we just recently saw for flat plate it was 2, so 2 is somewhere here. It's 100 times bigger, right? Or even 0.6 somewhere here is many times, tens of times, right? Around 30 times bigger than for typical value of airfoil. This is significant difference. It's a significant difference. Only at these values of drag coefficient we can have a sustained flight. So drag coefficient for aerodynamic body supposed to be small. Just a moment. So I have an animal who would like to enter here and listen to this class. Attend this class. So values of drag coefficient. Pay attention on this value compared to different reference when you make work one. It's important not to make mistake because otherwise could be problem to compare with the numerical simulation. Numerical simulation will also give you some estimation of drag coefficient, not very correct on inviscid simulation and much more correct on viscous simulation. As I told you, because viscous simulation provides shear stress calculation and it's the most contribution to drag coefficient. Always must be positive and small for airfoils and also positive but big for blunt bodies as a cylinder, sphere, or plates. 90 degrees angle of attack. Of course, for flat plate, shear stress coefficient is small. This one is for flat plate. You can see it's small, but not so much different than for airfoil. So you can see that it's comparable. 100s here for flat plate at most, right? But okay, of course, it's the biggest value, right? And this 100s, it's somewhere here, 001. So it corresponds to angles of attack somewhere close to 6, 8 degrees, right? 5, 6 degrees. So airfoil is not so bad from point of view of drag. Can be compared just to flat plate where drag is created just by friction. And then Anderson shows practical application of estimation of drag and its influence on various configurations of airplane. This is a very old airplane from 1930s, like 100 years old airplane, but it serves just like as a demonstration, XP41 demonstration that shows that when we are changing even a bit, not so much changing geometry of airplane, putting some additional instruments, some additional devices that usually are directed against the flow or perpendicular to flow, they interrupt the flow, disturb, and they have their own drag coefficient, quite big drag coefficient. But since these objects, these tools are small compared to all airplane, this change of total drag coefficient is not so significant, but is sensitive. Starting from completely paired airplane is airplane which has no additional instruments. We see that drag coefficient is almost 17 thousandths right? 17,000, and lift coefficient is 1500s, approximately 10 times bigger, maybe 9 times bigger, right? So lift to drag ratio is not so good. It's almost 9. It means that power of engine should be nine times bigger. Oh, sorry, power of the engine should be 9 times smaller than weight of this airplane. And then when we see addition of devices, each installation increase this drag coefficient, gives delta D to total drag coefficient, and it increases significantly, right? The total almost 50%. Oh no, not 50%, even more. A significant change of drag coefficient. And it shows that significance of estimation of drag coefficient even for small additional instruments, which gives a significant impact on the final drag and on the final thrust of the engine, which should be installed on this airplane. Of course, engine will not change. Engine will be the same. But what happens when drag coefficient is changing is changing maximum velocity, and it's changing stall velocity of this airplane. Okay, when drag is changing, it changes the flight velocity and can be a significant difference. Another, let's say, process that is explained is for supersonic airplane T-38 jet trainer, showing the zero lift drag coefficient variation with Mach number is another parameter that has influence on drag coefficient. One more time, I'm writing you that CD is a function of Reynolds number, but also Mach number and angle of attack. This is from Buckingham P theorem, as you might remember. So Mach number has a significant impact on change of drag coefficient for compressible flow. This zone, not just for compressible flow, but more even for transition on transonic flow, starting from approximately 0.8 and finishing 1.2, we see more than 2 times or almost 3 times change of drag coefficient and zero angle of attack. It's zero lift drag coefficient. It means that drag coefficient when lift is 0. It means that angle of attack does not, in a such way that does not produce any lift. It just measures drag, does not measure any lift, has zero lift. It's directed flap or wing has such a geometry that produces no lift, just produces drag to measure performance on zero lift. Significant change on transonic regime because at this point, as we discussed already, start to appear normal shock waves. Then these shock waves, they start to increase, right? Appear lambda shock waves, and after can appear a system of shock waves with big losses on transition from supersonic to subsonic region. So this transition, these losses of flow on shock waves, they result in significantly increased values of drag coefficient. When we are talking about small values of Mach number, and especially incompressible Mach number, we see that drag coefficient is independent on Mach number. Okay, Mach from 0 to Mach 0.3 is constant, and even though if we go further inside compressible flow until transonic region, we see that is still continuing to be constant, this drag coefficient continue to be constant. So this is important for also our understanding, because if we are, for example, studying, I had many such questions. Okay, professor, we have found this CD as a function of only Reynolds number, but do we need to find a function also that considers Mach number? And here you see direct answer that you do not need to search for drag coefficient as a function of Mach number if you work outside of this transition region, outside of transonic flow. If you are in incompressible or you are in compressible but not transonic, you do not need to find function on drag coefficient dependence. Okay, this should be clear. What from practical point of view also, what does it mean? It's very important, because it's easy to do experiment at this point here when we have extremely low Mach number, almost zero Mach number. We do experiment here and we measure what at this point our airplane has drag coefficient at this point. We measure. What does it mean? It means that we do not need to test in other points until transonic regime. It will have absolutely same independent on Mach number value of drag coefficient is same. Okay, absolutely same value. So we can reduce number of experiments significantly. We can reduce number of numerical simulations significantly when we would like to find drag coefficient, and we would like to find drag or required thrust of our airplane. We provide just one test or one simulation at conditions we are interested, or it's easier for us, and we can say in all this region from 0 to transonic will be absolutely same value of drag coefficient. Keep in mind following, that we just change Mach number. We just change Mach number. We need to keep same Reynolds number, right? So this is only discussion about Mach number. Do not forget that in Mach number we have velocity divided by speed of sound. In Reynolds number we have velocity, density, size, okay, and divided by viscosity. But in both of them we have velocity and we have velocity. Okay, when we change this Mach number, we also have to see that our Reynolds number is constant. This is extremely important to understand, that just changing velocity is not enough, that we must compensate in some way, and probably increasing velocity, we must decrease size of the body to keep the same Reynolds number. Okay, or we must change density in variable density tunnel to keep the same Reynolds number. So there are some aspects that must be considered. This graphic is only considering change of Mach number, but it does not consider change of Reynolds number. It means that Reynolds is constant for this graphic. It gives a difference. It's not so much simple, right? Just use another velocity and simulate, or just use another velocity and calculate. No. You need to keep Reynolds number. It means changing velocity, same time you change size of the body, or you change the viscosity, or you change density of fluid to keep constant Reynolds, because drag is significantly changing with Reynolds number, as we saw before. But is not changing with change of Mach number if it's changing independently on Reynolds number or with constant Reynolds number. I hope it's more or less clear. I would like to remind that you could ask your questions in the comments. Please let me know if you need to know something related to this topic, or you have another questions related to work one. I would like to remind you that on Friday we will talk only on practical applications and about work one. So please collect your questions. This Friday is important, very important to participate, because I think it will be very last. Let me check. Yes, it will be probably the last before you need to deliver work one. So this Friday you can ask all your questions about work one if you have some. I already answered a lot of questions on my previous videos, which you could also find. But if there are questions, I would be happy to answer, because our next practical class will happen only after 2 weeks. So this Friday is a good time to clarify everything you would like to know about work one. Okay, let's combine this, and I would like to answer all your questions and show you as much as possible how to do correctly and in a good quality study on aerodynamics. Okay, please tell me.
I have a question. What's the point to maintain the Reynolds number constant? I think I lost some part of the presentation.
Okay, thank you for your question. Let me. Probably here is not written. Here is not written. Here is written Reynolds 3 powered by 6 only on this graph. Let me use another color. Okay. For other Reynolds number, this curve would be different. Let's just speculate. It's not this. I do not remember exactly how is Reynolds number variation for this airfoil for other Reynolds number, but I will just make some speculation that if we change Reynolds number, the curve would be going like this. Okay, for different Reynolds 1, Reynolds 2, and okay, Reynolds n, different values. So curves will be different, and a lot different, not just 1%, 5%, because drag is formed mostly by skin friction. Drag is highly function of skin friction. This is why skin friction is strictly related, to Reynolds number, because it uses the same viscosity definition inside the skin friction and inside Reynolds. It has viscosity. So I can write that it's a function of Reynolds number. High. Okay, it influences a lot, the Reynolds number on the drag. And also angle of attack, as you may see from this plot. Okay, it's clear that drag changes from 4,000 to some 4 times, 5 times higher at stall conditions. So drag changes a lot when you change Reynolds number. But if you have constant Reynolds number, you can just change Mach number. It does not influence at all.
I see. All right.
Does not influence at all. So when you fix Reynolds number, you will just try to change Mach. You will see that no dependence. It means that we can test at small value of Mach. We will receive same drag as for high value of Mach until transonic flow, of course. Okay, so this is what was meaning, that once you try to change Mach, you can change only Mach. You cannot change Reynolds. So you need to compensate the change of velocity inside Mach number. For example, increasing of velocity, you need to compensate by decrease of size of the body. to keep same Reynolds number. Okay, I hope it's clear.
Yes, it's clear. Thank you.
Okay, thank you for your question. Second parameter is lift coefficient. For different airfoils, lift coefficients are different. The typical values are these, as you see on this picture. This NACA 63-210 is a very performant airfoil. It has at top some lift coefficient close to 1.4. Probably would be better to make just one line. Near 1.4 maximum. We can find more efficient airfoils on the market. Please, Guilherme.
Professor, I have a question related to the drag efficiency that you commented. Because in airplanes, it makes sense about the relation between drag and lift. But I was wondering about airfoils in rocket fins, because in rocket fins, lift would mainly be for the purpose of stability and providing actual spin. So would that relation of drag and lift still stand, or would it be better to analyze mainly drag on rocket fin airfoils?
I think it's a very interesting question, very important question actually, because in as you told, in airplanes, all wings are parallel to ground, so they must generate lift. And for rockets, they are used to control the flight, stability of flight. I think in details we talk about it in gas dynamics is when we finish studying theory of oblique shock and expansion waves, oblique shock waves and expansion waves. There we can quantitatively say how much is important these parameters, lift and drag. But now I can tell you the following, that both lift and drag are very important for rocket applications, for fins, because lift is a force that creates stabilization. I will try to make maybe here some on the corner, some small picture. Okay, I will do my best to draw. Not so good, not so convenient. Okay, maybe like this. Let's assume it's symmetric, because for rockets it's symmetric. Usually symmetric airfoils are used. When we try to change angle of this angle of attack, we will start to obtain stabilization force. The stabilization force will turn our rocket in one or other direction, because center of mass is at some point, much upper point, right? And since we have this lift force, let's call it still lift force, perpendicular to, or normal force, normal to horn, we still have distance between aerodynamic center or aerodynamic center and or center of mass, and this force created on the fin, because this airfoil is placed at the end of the rocket. We have a significant distance, so we can have significant moment of control of our rocket, depend on what is the purpose, to follow some trajectory, some specific trajectory, so it has servo or some actuators or pneumatic actuators. If it's just a question to have aerodynamically stabilized flow, it also can happen, because once the rocket is not going according to trajectory, for example, there is some side force. If the rocket is inclined, the side force creates lift, also creates lift, which is contrary to the action of wind, right? and it stabilizes the rocket. So lift force is extremely important. I think it's even more important than the drag. And the drag is something that must be taken into account in force balance. Thrust which acts in the opposite direction. It must be much bigger than this drag. Of course, this drag is very small at fins. It's very small for airfoils, right? And usually thrust is much bigger force. And the biggest, most significant part of drag is created by the head of the rocket by itself. But I think both of these forces are important. Lift is important to define control, or if control is active, is obvious that lift force must be determined. For control, if control is passive, should this force should compensate external influence, let's say external influence, when trajectory is not going, inclinating according to flow direction. And the drag is important, but not so much, for my opinion, in a total balance of forces. So both of these forces are important. I hope that is it. Bigger is the rocket, smaller are the fins. You know, on small rockets, fins are big, but on big rockets there are no fins, especially on the rockets which have thrust vector control by engine. Okay, but for small rockets, fins are essential, and I think it's important to estimate two perpendicular forces: force of drag resisting to thrust, and force of lift that helps to control trajectory. Okay.
I see. Thank you, Professor.
Okay, thank you for your question. Let me remove here. Typical variation of lift, typical values of lift coefficient, 1.2, 1.5. There are more performant airfoils, as I said. There are airfoils which have a lift coefficient 2. It's higher, right? ISO airfoils. For example, our competition team, Mammoets, they use airfoil which has lift coefficient 2. It means that, okay, you have very high lift created by size. It's very good from one point of view. Okay, it has some disadvantages which we will not discuss today, mostly related to other aerodynamic parameters, because lift is not the only definitive criteria. You must always see ratio of CL by CD, and it should go to possible maximum, right? And not just this, there are others. You need to have a momentum coefficient in some limits. If you have too much big or too low momentum coefficient, you will need to compensate momentum coefficient because it starts to rotate all your structure in one or other direction. You need to have a tail, for example, big tail that compensates a momentum coefficient. These three parameters are just from aerodynamics, but you know, when you design real structure, you need to consider structural strengths, you need to consider dynamic characteristics and the others. Storage, for example, if this airplane uses liquid fuel, you have to put tank in the wing, so must have sufficient volume and sufficient structure. And there are many other questions. Okay, just from aerodynamic point of view, you need to see these parameters as I showed you on this slide. They are lift to drag ratio and values of momentum coefficient. There are some very good, very performant airfoils with very high lift coefficient, but they also have a high drag coefficient. So lift to drag ratio is not so good. There are airfoils with a very good lift to drag ratio, but they have very high or very low negative momentum coefficient. Also not good, because you need to put additional weight, additional mass on tail to compensate this momentum. So always pros and cons, advantages and disadvantages. There is no aerodynamic structure which is perfect for all possible applications. For each case, we design a different airplane for each size, time of operation, for different velocities, for different altitudes of flight, for many conditions, not just from aerodynamic point of view, but also from many other points of view. No perfect airfoil, no perfect airplane, but life goes on, right? We have this is why we have advances in aerodynamics nowadays, new methods which give us completely new structures, better structures, more performant. Lift coefficient can be positive for positive angles of attack and for small negative angles of attack as well. And lift coefficient also can be negative for big negative angles of attack. It's normal. Okay. Sometimes lift coefficient can go through origin of coordinates, as you can see on figure 162. It goes through the origin of coordinates. This happens always for symmetric airfoils, and for some non-symmetric airfoils also may happen such thing that when you have zero angle of attack, you have zero lift. You do not generate lift. For non-symmetric airfoils, and in particular for cambered airfoils, they are curved in some way. Okay, this angle of attack, zero angle of attack, does not result in zero lift coefficient. Can be different. Okay, we can see some similarity between one picture and the other. For example, this cambered airfoil, we will study this cambered airfoil in future, looks very similar to airfoil with the flap deflection angle, right? The purpose is same. We have some part of airfoil which generates very good performance, lift to drag ratio, and we have very small part which is called flap to generate additional lift. With this angle of flap deflection, we also control level of lift coefficient. When this main angle is constant, this variation of flap angle creates to us all the control force on the airplane. This is how all modern airplanes work, right? Main part of the wing is having constant connection to fuselage, so it has constant angle of attack, and the flap is rotating, changing in negative or positive value lift coefficient, and with change of lift coefficient we have lift changing, variation of lift, not just lift coefficient, right? That's one of the ways to change lift, right? The most efficient, probably the most performant. Nowadays, flap is not just simple airfoil behind this wing, right? Nowadays, flap can have very complex multi-body structure that allows to perform very good efficiency. wing. About this, I think we will talk a bit later when we talk about flow separation. It will be a discussion. About momentum coefficient, usually momentum coefficients are small, relatively small. They are airfoils with the zero momentum coefficient. For example, theoretically, according to analytical model, all symmetric airfoils have zero momentum coefficient at 1/4 Hort. Theoretically, in real life, it can change, but it just a little. Right? You may find if you already have symmetric airfoil, you probably already found the momentum coefficient variation. You can see it very small, or you see it equal to 0. Okay. Symmetric airfoil have small value. Non-symmetric airfoil like this Mach 63-210, it has a small negative momentum coefficient. What is positive and negative, I think we already saw. And if I forgot to explain, just in a minute I will return back to discussion and show it. We see that for big variation of momentum is staying on the same sign. So for negative and positive angle of attack, momentum is negative. For other airfoils, it's positive. For another airfoil, can be changing from positive to negative. Okay, can be any variation. Usually, momentum coefficient is small. Has small value, can be some tens. Tens is very rare. Hundreds or thousands, very small value. Because if we have big value of momentum, as I already told, we must compensate by other part of the airplane is not good, is not efficient. So efficient airplane does not have big value of momentum coefficient, especially at 1/4 Hort. You have to also pay attention to this. MC divided by 4. It means that we have it exactly on the 1/4 Hort. I will try to find here where is this 1/4, somewhere here at this point. 1/4 Hort, 25% of Hort, somewhere there. As an example, I showed you airfoil here. For any airfoil, we find coordinates internet, so no problem to draw, to analyze, and to calculate at least geometry. Okay, end of part 1. As I promised you, I go back a few slides just to see where I missed definition of positive and negative momentum. It was probably here, yeah. Okay, what is, opa. Sorry, I have something. Program. Just a moment, I will restore my program. Sometimes it happens. Okay, we are back. Positive and negative momentum. It's a so-called sign convention. Is an agreement. Okay, an agreement that if we fix a point on the airfoil and forces will try to rotate in clockwise direction, our airfoil total momentum will be considered as positive. if for aerodynamic forces will try to rotate our airfoil in counterclockwise direction, momentum will be considered as negative. Okay, this is valid for any point. For example, we choose 1/4 chord and we see at which direction it rotates. This direction clockwise is positive. If I see rotation, or if I see negative momentum on graphic, I will understand that at 1/4 chord, my airfoil is rotating in counterclockwise direction. So very simple definition. In American literature is like this, but if you will study using other literature, please also need to see which sign convention is used. Usually it's like this, but maybe different. Always good to pay attention at this moment and to understand about sign convention for one or other reference publication. Okay, if you're using American literature for this, you can expect this sign convention. Please let me know if there are some questions. As I told you, this is the final lecture on Introduction to Aerodynamics, and I did not intend to give you second chapter. We will start second chapter on Thursday. Please write if you have questions, or say by voice if you have questions. I will be happy still to answer. Okay, I see no questions. Anyway, it's not the last moment, okay, when you can do it. If you will have questions about chapter 1 next time, I still can explain something. Please read chapter 1 if everything is clear, because it's the main information which helps you to make work 1. And to calculate all work 1, you will probably need just theory from chapter 1 of aerodynamics. This is all you need to know to make work 1. So to make work 2 is more difficult. I'm recommending you to see videos, and which I already have a lot, about work 2 and work 3. And on Friday, we will pay a lot of attention on practical applications. So I see no questions. I stop recording, and I would like to thank you for participation today, and we will meet after tomorrow for sure. Thank you very much, and see you next time.
Thank you.